Okay, let's do our notes on making electricity. So, the simplest version of a generator is to look at just a single wire. You saw in the little demos, I need lots of wire to really make a lot of electricity. But to understand the concepts, we're going to pretend that we're just going to take one wire and move it through the magnetic field, and that's going to be making our electricity. When you make electricity with a DC generator, you make stuff that's like a battery. But when you make it with a real generator, you're going to make alternating current. And so when we make electricity, we're going to create current that is set to alternate. We're going to use hand rule number 3. Okay, straight fingers, meaning the pointer finger, points to the field. Remember, that's always going to point, your finger is going to point to the south. Your thumb, instead of being the direction of the current, is going to be the direction of the movement. And then when you bend your fingers, there's our three-dimensional hand, our palm, or these 3 fingers, point the direction of the current. And again, if I use my right hand, it's current. If I use my left hand, and then, you know what we call these? These are gang signs, physics gang signs, so I can flash my signs at you. Anyway, let's practice. Now, this gets tricky on paper because you start to do physics yoga. So you're gonna see me flip the paper around a lot and get it in the screen, because instead of breaking your arm trying to do this, we just move the paper. So in these 2 cases, I show 2 magnets with the end view of a wire. Remember, we're always looking at the end of a wire. And I would have to move it. So let's say that in this case, I move the wire up. I want to know, the electrons, or is the current going to come at me with a dot X or dot X going away? So the first thing I'm going to do is I'm going to spin my paper around, because I don't want to look at the outer ones. It's only these 2 that count. The south is far away here, or on the far side, so I'm going to put my hand like this on the paper. And I'm making my thumb. My thumb is the direction of the force, and my finger is pointing, which was to the south, which was on the right side of this. And when I bend my fingers, you can see that my hand lifts up off the paper. My hands are pointing down. That is an X. All right, next one. North and south. I don't care about these. Again, I'm going to turn this to make it easier for my hand. Excuse me while I do this for a second. So I'm going to turn this. Let me zoom in a little bit. My finger is pointing to the south. I guess you need to see my whole hand. That would probably be better. Let's say I'm going to lift this one up as well. All right, my fingers are to the south, but you notice my thumb is not. My thumb has to match the direction that I might be lifting the wire. So I have to lift and flip my hand. So you need to be doing, I need to see you guys actually doing this at your seat during your notes. And notice when I bend my fingers, boom, they're pointing up to my face or to the sky. That means the current is coming at me, and we use a dot. Okay, so it's very similar to left-hand rule number 2, except we're only going to use this for generating current. So we don't just lift wires, we make them go in a circle. So again, this is the simplest version. So I'm going to use a pencil, and I'm going to lightly put in the magnetic field, like when we drew them way back with the iron filings. And they'd have little arrows that point towards the south. Now, notice that this particular one moves parallel, and this one, they move parallel to the field. These 2 move perpendicular. What happens when you generate electricity, you get maximum current at 90 degrees perpendicular, and it fades off to 0. Perpendicular, 0. Maximum, 0. Maximum. It constantly, that's alternating current. That's the kind of stuff we use in our house every single day. It's alternating. American generators make this circle 60 times a second. When you look up any of those devices, maybe when you looked up, you might have seen 60Hz. All of our electronics use that. I'm going to give these letters, okay? Let's call this position A, position B, position C, and position D. And of course, I can move those or just label it everywhere. If no current, there will never be any current on A or C because they are parallel. no current moves parallel to the field. Let's add that in. In order to find which one of these is the dot and the X, because they're going to alternate, I need to use my right hand. So again, my south is here. So I'm going to turn my paper. I'm going to ignore the outer. I only care about the stuff that's on the inside. This is south. I'm going to do part D. So I'm going to put my finger pointing to the south. There's my hand. Zoom in. This is matching here. And when I bend my fingers to point, they're going down. So this has to be an X. Probably looks like a plus sign right now. To do the other one, again, my hand's still here, facing the south, but the arrow is the other way. So I have to flip my hand and my fingers point up, oops. So that's a dot. Okay. Let's put maximum current at 90 degrees, or you guys know the perpendicular sign. The other thing you need to know, and I guess I'll use my highlighter just to have this. This is just to establish a direction. We think of negative for the current coming towards me, and we think positive. I always tell everybody, think of the X as sort of a crooked plus sign, because we're going to graph this and we need to have some numbers. Well, first of all, A and C make no current. You know what, I'm going to use my highlighter. A and C make no current. D was a positive maximum, so it would be up here. Oops, we're at this A. B would be negative. So our curve will look something like this. Now, this curve can look different depending on where you put the letters. So there's all different versions of this, but all of them will have some kind of up and down, and this is what we call alternating current. Let's go into the actual generator part, so zoom in a little bit. Let's use the highlighter. First of all, there's two kinds of generators. Most of the generators that you use at home during a hurricane are AC, because that's what we use at home. First of all, they always have a magnet. Generators always have magnet, doesn't matter which one you look at. Okay, they're gonna have all the same parts except for one. They're always gonna have a coil of wire. That's what spins. It's usually not just single wire. They're gonna have brushes. Those were those little connections. If I remind you back to this, these little connections here were touching the movement. Those are called brushes. And then the connection, depending on whether it's AC or DC, they either have a commutator or slip rings. This is the most common for us because we use AC generators. All right, so what do they both have? They both have magnets. They both have coils. They both have to spin. They both have brushes. Generally, we talk about slip rings here. The one thing that's missing from this picture, which would normally be in a generator, would be in here. I'm just going to scribble it. There would be some kind of iron or metal, because you're going to need that to make the field stronger. So Faraday is the guy who gets credit for basically saying that the opposite of Ørsted was that if you instead run electricity, I'm just going to give a quick look up on Faraday so you can get the same kind of information on him. All right, here's a little picture, a little shout out to Faraday. Michael Faraday, let's see, he was born in London. We're talking 1791 to 1867, so not terribly a different time than Ørsted. English scientist who contributed to the study of magnetism and electrochemistry. His main discoveries include the principles underlying electromagnetic induction. So Faraday, think of him as doing the opposite. So let's go give a shout out to Faraday. Put that up on the top of your paper. The other one we gave a shout out for was Ørsted. instead of having electricity make magnetism, we have magnetism making electricity. So you can see how they're a little bit different. So here's his law. Okay, so this little scripty E guy stands for electromotive force. Sometimes we call it EMF. It's measured in volts. It's just how much voltage you get to make. I mean, the power plant makes lots of volts and they step it down and give us. B is the field strength of these, like of the magnets, how strong they would be. And of course, you can see in theirs, they didn't label the other ends of their magnets. They just labeled the parts that they cared about. The velocity, the faster the coils spin, the more electricity you're going to make, and the length of the wire, the more wire. So let's try a couple practice problems. This one says, what is the EMF generated? I'm sure I have my calculator here. There it is. So EMF equals BVL. All right, so we have 1 meter, 20 meters per second, and 2 times 10 to the negative 4th Tesla. 2 times 10 to the negative 4th times 20 times 1. Let's see what we get here. 2 second, you have to turn it on. 2 second EE negative 4 times, what was it, 20? Yeah, 20 times 1. We don't need to do that. So 0.004 volts. That is not a lot of electricity, is it? That's a weak magnet. How fast must so here's the length. The length is 10 meters. V is my question mark. Be moving in the Earth's. Okay, so remember, every time I tell you about the Earth's magnetic field, it's roughly 5 times 10 to the negative 5th Tesla, also called 50 microteslas. How fast does it have to go to make an EMF of 1 volt? All right, EMF, BVL. So 1 equals 5 times 10 to the negative 5th times V times 10. All right, so, well, 5 times 10 to the negative 5th times 10 is going to be 5 times 10 to the negative 4th, V. And then if I divide it out, we'll do it like right here. Move it a little bit. Clear. 1 divided by 5, second EE negative 4. We're going to get 2,000. So obviously, that's really, really, really fast. 2,000 meters per second. Okay, if it weren't for magnets and wires and moving them, we wouldn't have as much electricity. All right, we're going to do some practice with these.